Hello everyone, welcome to Wave2Wave's webinar series on automated fiber switching technology and applications. We invite you to view our complete series of webinars to get the full overview of beneficial impacts of automated fiber switching in various deployment applications. Today, we will look at introducing automated fiber switching as an enabling ecosystem component for mobile networks. Today's webinar will show the benefits of automated fiber switching technology when utilized in multi-standard processing applications that incorporate digital radio signal transport over fiber. This architectural approach serves as the base foundation of emerging mobile network architectures such as LTE Advanced and 5G. Next slide, please. We'll start with a discussion on mobile network architectural evolution and industry dynamics. This is followed by a look at centralized cloud radio access networks, or C-RANs, as an architectural design approach for mobile network operators, along with some of the challenges of these emerging deployments. We will then look at integrating automated fiber switches into these emerging networks and the resulting benefits in both CapEx and OpEx savings. We will conclude with a brief overview of software-defined networks, or SDNs, and how automated fiber switching improves SDNs when applied to wireless C-RAN deployments. So let's get started. Next slide, please. Mobile networks have undergone significant changes over the last decade, and the rate of change is accelerating. Since the introduction of smart devices and exponential growth of data traffic, mobile operators have faced challenges in making networks more dense, increasing efficiency, improving user experience, and capturing additional profitable opportunities. They have attempted to keep up with changes by deploying new generations of network technologies and architectures at an accelerated pace, from 2G to 3G to LTE, and now LTE Advanced and 5G. The exponential increase in mobile data traffic over the past few years has been astounding. This trend is still strong, with mobile traffic expected to grow by a factor of 8 times between 2015 and 2020, according to Cisco in its VNI Global Mobile Data Traffic Forecast. As we just alluded to, densification is an acute challenge from both OpEx and CapEx perspectives. However, it also presents tremendous opportunities for mobile network operators with respect to revenue potential. The world is going mobile, and MNOs have a great opportunity to create new business models if ideal ecosystem components are utilized to their full potential. Next slide, please. In both traditional macro base stations and distributed base stations, the cell sites are very expensive. The expense is driven by the high cost of individual radio processing base station equipment. In addition, traditional deployments, ancillary costs such as construction, electrical power, real estate, and equipment testing cannot keep pace with the growth of densification. Therefore, MNOs are under tremendous pressure to reevaluate their macro cell footprints and deployment practices, leading to development of denser, more flexible, and cost-efficient networks, and to also consider integrated fixed network and mobile network architectures. A promising approach is to inject smaller cells and baseband processing equipment pooling into a cooperative wireless and wireline heterogeneous network environment. The interworking of micro and fixed network transport significantly improves the mobile network cost performance ratios with both capital expense reductions and enhanced equipment operational capabilities. Next slide, please. If we look at cost comparisons of traditional macro base stations versus C-RAN applications, C-RANs yield significant savings in both construction and power costs alone. That's outside of equipment savings gained from centralization, as we will see later in the presentation. It's no wonder C-RAN deployments are gaining momentum, particularly with 5G on the horizon. To maximize network access utilization and simplify infrastructures, MNOs are focused on the convergence and integration of wireline and wireless networks. Seeking cost-efficient and geographically dispersed mobile transport, especially within the classic telco distribution network, it becomes essential to fully leverage the economics of C-RAN architectures. Next slide, please. When we speak of C-RANs, it has several quote-unquote C characteristics, namely centralization, cooperative radio, clean system, and cloud computing. We centralized several baseband processing units to a central baseband processing equipment pool and used real-time cloud computing technology approaches and techniques to digital signal process different radio standards. The distributed radio remote units, or RRUs, collaborate with each other to reduce interference for a clean system target. By clean, we are referring to minimum cross-user interference. In traditional macro base station processing, each station processes signals separately, so the signals from other stations can interfere with users, especially at cell site edges. A C-RAN architecture with proper ecosystem components can also support placing baseband processing units in a virtual processing pool while supporting signal data exchange. That way, different baseband processing units can share information and process user signals jointly to reduce cross-user interference. This requires a very strong communications protocol to ensure the baseband processor communicates with minimum latency to the RRU. Next slide, please. The communications protocol standard between the central baseband processing pools and RRUs is referred to as the Common Public Radio Interface, or CPRI standard. CPRI was established to define a publicly available specification that standardizes the protocol interface between the baseband processing unit, sometimes referred to as the digital units or DUs, and RRUs. To manage the connected radios, the DU uses the CPRI communications protocol for the DU-RU interface to transfer synchronization, digitized radio signals, and control and management information. The CPRI protocol standard requires a full duplex serial data stream with a transmit interface and a receive interface. For a C-RAN-based architecture to perform well, it is important that the overall CPRI transport network is designed to keep communications latency as low as possible. In fact, bit rates can approach almost 10 gigabits per second, so fiber is the transport of choice due to latency and bandwidth needs. Given this point, the best facility for CPRI transport is dark fiber, because encapsulating CPRI into another protocol may introduce latency and jitter. Next slide, please. As we saw in the previous slide, CPRI over fiber is typically used to connect baseband processing units to RRUs, and this connection is often referred to as front haul. In some architectures, BBUs are linked over backhaul core networks and share information, while in others they are simply located within the same building. Now, scaling the network to several dozens or several hundred RRUs require many fibers for direct high bandwidth CPRI connections. For example, in an LTE system with 20 megahertz bandwidth and RRUs equipped with 8 antennas, which is the most common scenario, the CPRI data rate between 1 BBU and 1 RRU for 1 LTE carrier transmission is as high as 9.8 gigabits per second. In addition, the prevailing engineering guideline is to design the front haul network such that one-way latency is below 75 microseconds. It is important that a front haul solution provide communications backup mechanisms in case of link failure. Given these requirements for both uplinks and downlinks, a minimum of 4 physical fiber connections are typically required with a minimum bandwidth of 9.8 gigabits per second each. As a result, it is necessary to find an optical transport solution between cloud and centralized DU pools and RRUs that consume as few fiber resources as possible, since a radio tower site can consist of at least 3 sectors, each supporting at least 1 carrier. One tower site can require a minimum of 12 fiber links. As we will see, the best options for CPRI transport multiplexing are coarse wave division multiplexing, or CWDM, dense wave division multiplexing, or DWDM, and passive optical network, or PON solutions to reduce fiber counts. Next slide, please. CWDM technology opens new possibilities for a cost-effective convergence with C-RAN, since a large number of CPRI signals can be transported with a small number of fiber cables by using wavelengths and PONs instead of dedicated fiber cables. CWDM systems allow multiple wavelengths to be transported on a single fiber by using matched wavelengths at both ends of the link. Typically, up to 16 CPRI wavelengths can be combined on the same fiber using passive or non-active CWDM components. The downside of CWDM is there is no one-for-one protection, and scaling to hundreds of CPRI links becomes an operational challenge without the simple and cost-effective addition of an automated fiber switching component such as Wave2Wave's Roam 500 product. One could argue another CPRI transport option is active transport DWDM products, which have built-in one-for-one protection. However, traditional transport DWDM systems were designed to address a different kind of fiber transport problem. They are designed to transport wavelengths over very long distances with appropriate processing features and economics. To achieve this, a G.709 digital wrapper is inserted into the bit stream to provide FEC, or forward error correction, and OAM, or operations administration and management functions, and active optical amplifiers are used to boost the signal strength. This can add 40 microseconds of latency to the link. Since CPRI already has its own built-in FEC and control plane, adding this extra content is to some extent redundant. Some transport DWDM systems can disable the FEC function, but still create about 8 microseconds of latency, which is equivalent to subtracting a mile of fiber from the traditional telco fiber distribution network route. This affects the entire engineering planning scheme of the outside plant. So the best option is still to utilize an automated fiber switch component to provide both protection and flexibility capabilities, which also does not affect outside plant engineering. Next slide, please. As we said earlier, centralization is the first critical step of C-RAN deployments. Recall that centralization aggregates different baseband processing digital units, or DUs, into one shared pool or facility. Specifically, the DU is the part of the C-RAN that MNOs move to a central location to serve multiple RRUs. Recall these network constructs virtual DUs. That way, MNOs may use a pool of DU equipment within a DU equipment rack or room to service more than one set of RRUs. To facilitate dynamic scheduling of resources for virtual DUs, an efficient reconfiguration approach for fiber interconnects is needed amongst DUs. This requires a fiber management flexibility point between the WDM MUX and the DU pool. This network architectural design provides a reconfigurable layer 1 switching capability that allows cross-connect management processes to be automated. The MNO's orchestration layer, be it automated or manual, can make fiber connection configuration changes within the pool of available DU resources. This also creates an audit trail for new business models such as DU processing as a service or on-demand resource spin-up billing services. In addition, according to the requirements of Next Generation Mobile Networks, or NGMN, the DU cloud should work with a small number of DUs that are in a malfunction or down state, for example, 10% failures. The combination of an automated fiber switch unit and virtual DU equipment controller could provide a backup DU. The automated fiber switch fabric, for example, Wave2Wave's Roam 500 product, enables flexibility in deployment while simultaneously supporting the reliability requirements regardless of DU equipment placement. Next slide, please. Before going deeper into critical ecosystem needs, we should spend some time appreciating the ultimate objective of C-RAN deployments. Recall that with traditional base stations, different baseband processing DUs are separated and each DU supports their own RRU. However, DU resource sharing and consolidation is one of the key features of C-RAN for cost and power savings. Therefore, dynamic DU task and load migration is a key technology cornerstone to resource sharing and consolidation. C-RAN then adopts general purpose processors to replace conventional closed hardware baseband processing DU systems. Each baseband signal type is processed through a software-defined radio, or SDR, baseband processing DU, based on virtual machine or VMDU platform. As with new IT methods, VMs are treated as independent operating environments with virtually independent CPU and I/O resources. For example, one DU processing unit for one sector of SDR processing could run in a virtual machine environment. Furthermore, some core network applications and services can also run on this DU cloud application, independent of signal processing in different VMs. The goal of decoupling baseband processing from RRUs is to enhance redundancy and maximize operational reliability. And for that, we need to deploy SDR equipment banks in a VM scenario. Next slide, please. These VMDU nodes are in the same rack, room, floor, or building to form a DU hotel. In this way, C-RAN deployments facilitate implementation of collaborative wireless radio networks to reduce interference and improve system performance. This also enables a DU cloud for providing baseband processing resource aggregation and pooling. Different radio protocol technologies can be implemented on SDR DU VMs within the C-RAN server farm network. VMDU pooled equipment coupled with automated fiber switching products allows expensive baseband processing equipment to be more effectively shared, which reduce capital and operational expenses. Without the AFS, increasing the size of C-RAN VMDU clusters makes it very difficult to switch data from an arbitrary RRU to any VMDU. Additionally, when the size of the C-RAN reaches a certain level, for example more than 30 sectors, the resource sharing gain may become flat or marginal without an AFS. Therefore, it's not practical nor economical to deploy a high-speed non-blocking mesh DU cloud without an AFS. Let's take a look at an example automated fiber switch technology approach to better understand its place in the C-RAN architecture. Next slide, please. An automated fiber switch is simply a switch that accepts a fiber interface at one of its ports and connects it to another port based on software-enabled patch connection decisions. There are two kinds of fiber switch core technologies, namely OEO, or optical electrical optical, and OOO, or optical optical optical. An OEO switch requires the light signal to be converted to an electrical signal to be processed and switched before being converted back to a light signal. On the other hand, OOO technology is done purely through photonics without conversion. Currently, the speed of fiber switching devices depends on the materials used to make the switch, the principle on which the switch operates, and the design technology. Although speed is an important parameter, one should also consider other parameters, particularly for wireless front-haul CPRI applications. These include latency, optical loss, dispersion, reliability, stability, switching matrix size, external voltage, if any, temperature dependence, physical size, and cost. As you can see, fiber switching devices can be modeled after a typical any-to-any port switch model. That is, in-input ports and in-output ports with a cross-connect matrix that defines the connectivity between input and output ports. For those of you inclined mathematically, this model can be represented by a classical matrix relationship. Let's take a look at the next slide. This is an illustration of the mathematical model of the matrix of an optical switch device, where I sub n is the amplitude of light at input port N, O sub n is the amplitude of light at output port N, and T sub n is the transmittance matrix. In general, the transmittance terms T sub n are functions of latency, absorption, dispersion characteristics, etc. of the optical connectivity path. Ideally, the T sub n terms are 1 or 0 respectively, signifying no impact or impact of latency, insertion loss, connectivity loss, dispersion, and so forth. We encourage engineers to consider this model and these factors when investigating automated fiber switching products. Let's go to the next slide. It is imperative for MNOs to explore systems that reduce CapEx and OpEx in order to maximize profits. Additionally, agile, flexible, and scalable network solutions are also essential. The only viable approach that satisfies all of these business requirements is a software-defined network or SDN-based C-RAN model. An SDN C-RAN provides great benefits in controlling ongoing operational costs, improving network security, network controllability, network agility, and RRU connection flexibility. You may recall from a previous slide that VMDU nodes can be in the same rack, room, floor, or building to form a DU hotel, given a high-speed, low-latency interconnect between them. An SDN C-RAN architecture based on automated fiber switching could then address capacity and coverage issues, network self-optimization, self-configuration, and self-adaptation using software control and management orchestration. Next slide, please. SDN C-RAN networks that include automated fiber switching, such as Wave2Wave's Roam product, offers dynamic fiber cross-connect capability at layer 1. With patented mechanical latching technology and fiber management, making connections within Roam are implemented remotely, precisely, and robotically. Roam enables physical fiber connections to be made automatically, quickly, and without on-site manual intervention. In other words, Roam provides fiber network connections anytime and across any fiber-based network, be it PON, WDM, or dark fiber applications. By the way, in addition to automatic fiber cross-connects, C-RAN AFS equipment requires high optical performance such as low latency, low insertion loss, high return loss, and transparency to optical wavelengths. Let's also not forget the fiber connection should be self-holding even in power loss scenarios. All possible with Wave2Wave's Roam AFS product. Finally, the Roam product does not inject extra OEO processing and multiplexing into the communication stream, thereby avoiding any unnecessary latency due to electrical signal processing. This is a critical and important capability when engineering CPRI communications transport networks. Next slide, please. So to summarize, both mobile network operators and telcos are faced with a very complementary set of challenges and opportunities. With growing demand for content-rich communications and cloud services and the Internet of Things, mobile and fixed networks are trying to keep pace. This trend results in a highly diversified architectural landscape, which is ideal for software-driven automated fiber switching components. With the increase of cloud size and use of AFS, operators can install more automated SDN VMDU clusters than with manual processes and procedures. Roam automated fiber switching co-located with centralized VMDUs provide DU equipment pooling gain to more efficiently utilize DU equipment and reduce capital costs. Therefore, the same number of RRU sales can be supported by a fewer number of centralized VMDUs. Deep penetration and large-scale deployment of micronodes in today's fixed networks can be leveraged and matched to distributed wireless sales that are being positioned closer to the end user. We anticipate that in many instances, the fixed access network will be used to transport mobile traffic. Where this is possible, it avoids creating separate dedicated networks for front haul, providing reduced OpEx and CapEx for mobile network operators. Additional new business paradigms automated fiber switching enables include faster time to revenue, reduced provisioning times, increased customer satisfaction, remote installation testing and troubleshooting, efficient use of CapEx in central office space, and cost-effective open network access business models. With all these benefits and more, the AFS is truly a key ecosystem component of any mobile wireless network deployment. Thank you for joining us today, and please feel free to send any questions you may have to info@wave2wave.com. Thanks again.